In this video, we'll cover section 11.10 and we will finish our study of Calculus 2. Now, this is going to be a fairly lengthy section. This is going to be very similar to section 11.8 in that we have a lot of material that we have to discuss, but then at the end, what are you actually going to be required? What are the types of problems that you will need to be able to solve? What you'll be able to do? We'll get to all that, but you have to be patient. You can't jump to the end. We have to see where all of this work develops. So, section 11.10, we do our last section discussing power series. Both this idea of Taylor and Maclaurin series, they are both examples of power series. So let's start off right off the bat with that. So we're going to be looking at some function f of x that can be written as some power series centered at A. So if we expanded this, we get c sub 0 plus c sub 1 x minus a to the first power plus c sub 2 x minus a squared plus c sub 3 x minus a cubed, and so on. So that is our standard power series, and we're looking at this power series representing this particular function. So all we need right now is just that a power series that specifically aligns to a function is referred to a Taylor series. So that's all it is. A Taylor series is just simply a power series. We just use this expression when you'll see in just a few moments, we'll have a technique, a tactic to get to these coefficients, these c sub n's, the sequence of coefficients in front of the x terms. But it's a Taylor series when it is centered at x equals a. And if we call it a Maclaurin series, the only difference between the Taylor and Maclaurin series is that a Maclaurin series is always centered at x equals 0. So even so far what we've done, the power series work, we've had series centered at other values, but a lot of them were centered at 0. And then section 11.9, pretty much all the power series that we found were Maclaurin series because we were always ending up with that, x as a part of our r term. So it was x over 4 or 2x, things like that. So the radius might be a little different, but just so many that we've done so far have already had a center at 0. And that is when we specifically call it a Maclaurin series. Now, these are just two mathematicians. This was named after them. So there's nothing else special about that. So again, they're both series. And if we ask about a Taylor series, you will be given that center value. And if you're asked about a Maclaurin series, well, it's automatic that the center is 0 for that series. So, a little bit of information, but now what we get, if our function has a Taylor series, if that is true. Now I'm writing Taylor series, but again, Maclaurin series is just a special case. A Maclaurin series is a Taylor series centered at 0. That's all. So by saying this as if it's a Taylor series, it covers a Maclaurin series as well. So if my function has a Taylor series of this form, and they talk a little bit about convergence values in the book as well, where it converges when the absolute value of x minus a is less than some value r. But here's the main point. If we have a Taylor series, then the c sub n, that sequence of coefficients, all these multipliers out in front of all the individual x terms, those c sub n's are equal to the nth derivative, that's the notation for the nth derivative at the specific value a. Again, that's center a, that's the same x coordinate here, all over n factorial. That is a huge key to this upcoming section. So when we try and find Taylor and Maclaurin series, that's what we're going to be doing a lot of. Writing out these terms so we could see what these actually coefficients are, and then we can go back and try and find the general formula for those coefficients. Now, this is the general formula, but we're going to make it specific to each individual example. So that's where everything gets started. We start off with this new idea, so it seems new ideas, but all this is just trying to give us a technique to find this individual power series. So we saw in 11.9, if we had functions of a very specific form, if they could be rewritten in some way in that a over 1 minus r, then we could write it as a corresponding geometric series. That a over 1 minus r is the sum of a series a r to the n. So we've already seen that. But now, for any other one, if it's not of that form, well, and also we saw if it's either derivative or antiderivative had that form, we could use that, get the power series for that form, and then take the corresponding derivative, antiderivative to get to our new function. We could do that same derivative, antiderivative on the original power series to then get the new power series. So we've already seen that. But now, if we're just starting from scratch, this will be a way for us to write out our terms and then find the general formula. That's the direction we're going. But now just a few little details that we have to discuss before we can actually start using that and start seeing all the different problems, the different situations that we need to be able to understand and sort our way through. So they talk about all functions have these ideas, and this is called a Taylor polynomial. And for notation, t sub n, where, if I want t sub 3, I would just look at the first 3 terms. That would be the Taylor polynomial. T sub 2, would go out 3 terms. T sub 3, we're using the same n here that we did here, and since we started with n equals 0, we'd always go to that. Again, if n is 3, that would really end up being 4 terms. So we can always write a Taylor polynomial, and there are a few problems that just ask for that. What is the Taylor polynomial for this function at this center? And they give you an n value, so it's just writing out the right terms. The x minus a, well, the a was given, so just keep the powers in order, and then go through and do this work, and you get your coefficients, and that's it. But now again, the extra work, the extra idea kind of behind the scenes. All functions can be written as a combination of the Taylor polynomial plus what we call a remainder polynomial. This is similar, not exactly the same, but similar to partial sums plus remainder, all to give you the final sum of a convergence series. So it's kind of similar here. So all functions can be written in this way. But now, if r sub n, if that remainder polynomial goes to 0, then the function can be written as its Taylor polynomial, and that's it. This, if you're following along in the book, page 799 just covered a lot of this introduction, and we'll see some more specific work. But then on page 800, that's where they start talking about some of these. Actually, I'm sorry, it's 801. They start talking about if f of x equals this, and then the limit of this goes to 0, then that f of x is equal to its Taylor polynomial. And the last quick thing I just want to point out, they mentioned Taylor's inequality. That if you go on to a higher level math class and advanced calculus, not Calc 3, but some schools call it advanced calculus, others call it a real analysis class, you may have to do a little bit more of the proof work here, and that's where they give you Taylor's inequality, that this remainder polynomial, the absolute value, is always less than or equal to some value m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. All of this is trying to give you a key to be able to determine if this goes to 0. If this goes to 0 and this is less than that and absolute value keeps it all positive, then this goes to 0 as well. And the last little key, oftentimes when you're trying to solve this value, it doesn't matter what m is, because m would just be some number. M comes from the idea m is smaller than the absolute value of the n plus 1 derivative. Oops, close that bracket. So there's just some value m, but m is just some number here. So the last little result, and again, this is really just for those who go beyond into some upper level class, just so you've seen a tiny bit of this. How would you know this goes to 0? You'd actually focus on this. You take this limit as n goes to infinity. You'd have to do a little bit of work to figure out if this value m exists and what it would be based on that specific function and its derivatives. But once you establish that, then we also get one other result that's a little strange. That as n goes to infinity, it doesn't matter what x is. X to the n power over n factorial always equals 0. That's not obvious, right? If you just think of this as 2 to the infinity over infinity factorial, looks like you're getting a lot of infinity over infinity. That's where a lot of people want to try and apply L'Hopital's rule, but you can't apply L'Hopital's rule to n factorial because there's no continuous function to go with it. So this is just a good known proof, and this almost always helps you when you're solving this little piece. If you're trying to show this goes to 0, you really are hoping that this goes to 0. There's a little bit of a squeeze theorem here. 0 is always smaller than or equal to the absolute value of anything, which if this goes to 0 and this is already 0, then this squeezes to 0 as well. And how would this go to 0? Oftentimes, it's based on this limit value. So, like I said, there's definitely some behind the scenes work that's going on here, but that's what I wanted to discuss quickly, but kind of move through fast as well. So now we could really focus on, so what do we do with this? And it really comes back to this. So all the stuff I mentioned here, it's good information. All functions can be written in this form, and if the remainder goes to 0, then the Taylor polynomial is, then you have that perfect power series representation for that particular function. But we're not worried about this part. That's just some quick information. Now let's come back to the actual work. So let's start off. Let's find a few Maclaurin series. Let's find the Maclaurin series. So again, you automatically know A equals 0, right? We already know that that center value is 0. Find the Maclaurin series for, we'll do two problems here. We'll do one, A of x is e to the x, and 2, we'll do b of x is sine x. Actually, while we're at it, 3, let's also include c of x is cosine x. So, how do we go about doing that? I'm going to do these Maclaurin series, and then the Maclaurin series is done for these three functions. You could completely copy and mimic this, but what I really want you to realize is I'm going to do it for Maclaurin series, and I'll come back and explain why I'm doing it for Maclaurin in a few minutes after we get through all this work. But you should be able to mimic what I do here for any Taylor series. Just note, and I'll do one of these after we get through this, but for a Taylor series, I have to give you the center. Okay? For the Maclaurin series, again, that's not really part of the directions. That's just a reminder. Let me even just cross that off. So there's your full directions. Find the Maclaurin series. That's all the information we get. So problem number 1. We had a of x was e to the x. So e to the x is going to be equal to some c sub 0 plus c sub 1. Again, my center is 0, so x minus a is just x. C2x minus a squared is x squared. C3x minus a cubed would be x cubed. And that continues. And again, this comes right back from page number 1, where my c's are going to come from this. So c sub n is the nth derivative. Here we know a is 0 over n factorial. So c sub 0, one tiny bit of notation. The nth derivative. So c sub 1 will have f first derivative. C sub 2 will have f second derivative. But the 0 derivative is the original function. Oh, I used function a. Let me stick with my notation. This will be a nth derivative at 0 over n factorial. So this will just boil down to the original function, n divided by 0 factorial. And that's it. So c sub 0 is 1. C sub 1 will be the first derivative evaluated at 0 over 1 factorial. Well, if a, this is where this is a very nice problem. A is e to the x. A prime is e to the x. A double prime is e to the x. A triple prime is e to the x. So this first one, any derivative is still just e to the x. So evaluating that at 0, I still get e to the 0. 1 factorial is 1. So coincidentally, we just get 1 again. C sub 2, the second derivative at 0 over 2 factorial. So 1 over 2 factorial, which is 1/2. One more for good measure. I'm trying to find a general pattern here. That's what I'm hoping to have happen here. So just like we always saw, whether we were writing it as a series or we were just looking at a sequence, you need at least a few terms to try and see and establish the pattern. Well, there's 3. There's not much going on with C0, so I kind of have 2. So hopefully this will be enough. Some people have to go a little further, but this first one's not bad at all. The third derivative at 0 over 3 factorial. That's e to the 0 one more time over 3 factorial. That is 1/6. So now, if you just fill these in, 1 plus 1x plus 1/2 x squared plus 1/6 x cubed. If you went and found C4, you would get 1 over 24 x to the 4th. Maybe some people are seeing the pattern, but a lot of it is already done. We know the series is going to start at 0 to infinity. X minus a to the n is just going to be an x to the n. So again, it's just these coefficients out in front. And if we clean all these up, maybe you don't see a pattern. But if I don't clean them up, 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial. Generically, C sub n is just 1 over n factorial. That is the power series for e to the x. Again, those Taylor polynomials, you'd be doing this work, but if they wanted T3, 0, 1, 2, 3, that's the third term up to the third power. Again, it's really the fourth term of this polynomial. They're still just x's to powers, all addition, maybe some subtraction, but here all addition just mixing in. So that's it. You would just find that many terms and you'd be done. But to say to get the full Taylor series, or again, we said specifically here Maclaurin series, hence A was 0. We had to keep looking. Don't just find a few terms, find enough terms so you could find the pattern. That is the power series for e to the x. For radius of convergence, now you've got a power series, and we don't really have any shortcuts. This is not like 11.9 where we were using the sum of the geometric series. So how do we figure out the interval of convergence? You'd go back to 11.8. You'd look at this, you'd think about appropriate tests. This would be a ratio test. That would be the ideal way to solve it. Solve the ratio test. I'm not going to do it, but I'll tell you what will happen. You'll take the ratio test, x to the n plus 1, absolute value on the x, n plus 1 factorial, divided by this, absolute value on the x. A lot will clean up. You're going to end up with an absolute value of x over n plus 1 when you clean it up. And as n goes to infinity, that goes to 0, is always less than 1. This will converge from minus infinity to infinity. So some people, they look at the work we did in 11.9, and we even kind of mentioned it. Some people are like, okay, that's the power series, but that's the power series for, it only works for x is -1 to 1 or x is -2 to +6. It felt limited. So we could always play games to move that interval, but to realize not all of them are that necessary. This would work for every value of x. Now I want to do and show you sine and cosine just to show how those work. But again, we'll come back. We'll talk a little bit more about this. I do want to mention this is a very common spot where people say, or where a lot of people start to realize, this is how calculators work. How does your calculator know what e to the 0.45 power is? Or, not that this is the same thing, just as another one, e to the square root of 2. How does your calculator know that? It knows this. It plugs that x value in, and your calculator is just basically it's an adding machine. That is one of the best features that any calculator has. So our modern calculators have things like this. Now, not all of our calculators use power series. Some of them have other ways to approximate, but not just random approximation. Really, really good ones that are accurate to multiple decimal places. But this is where a lot of them could get started. They just may have a better way. How do you figure this out? You plug it in. E to the 0.45 power is 1 plus 0.45 plus 1/2 times 0.45 squared, and that would continue. Similar here, this would be 1 plus the square root of 2 plus 1/2 radical 2 squared, and that would continue. And again, our calculators can just have some sort of like a rounding program built in. They can also have extra formulas for error that we've talked about before to know, okay, if you want to be accurate to the 10th decimal place, well, you have to at least go out to the 1/1,000,000th term. So there's other things calculators can do, but that is a real powerful aspect. Okay. And like I said, we're not done. We're going to see a lot more of what we can do with power series. This is now that we get here, some people still at the end are like, okay, that's nice, but still they have this overwhelming feeling of, so what? Who cares? What does that do? Well, we're going to realize that, again, polynomials, that's what these are. This, again, keeps going plus ... forever. If we wanted a Taylor polynomial specifically to a point, it would stop. But in general, the Taylor series goes on forever. But it's still a bunch of nice terms connected by addition, subtraction. So derivatives, antiderivatives, limits, so many things are made so much easier by being able to have this form. So that's what we're going to come back to. And that's ultimately, while there's a lot of other reasons why we've covered Chapter 11, that's kind of like the big, overwhelming what we've been aiming for. But again, more practice. Problem number 2. Still finding the Maclaurin series, so A is 0. But now for problem number 2, we're looking at sine x. By the way, the book, examples 1, 2, and 3, I'm almost positive are the exact same problems we're doing here. Normally, I try and stay away from doing the exact same problem. But again, after we finish this work, I'm going to show you this chart. I'll show you right now. I'm going to show you this chart that you find in your book. And it has known Maclaurin series for all these base functions. We've just found the Maclaurin series for e to the x. We knew this one. We're going to find these two. We found both of these two in 11.9, and then we'll finish up with this one. We'll say this one very quickly, but these are going to be our main focus. That's ultimately where we're going. So that's why I don't want to just make up random examples. I want you to see these exact few examples. So now we're finding the Maclaurin series. So there's my directions. Again, that means we know A is 0. And I could do something similar like I did up here, but let's really cut to the point. We need to start figuring out what's going on with these coefficients. And in order to do that, we're going to need the derivatives. The reason why number 1 was so nice was because the derivatives were so simple. The derivative of e to the x is exactly itself. But now that we're dealing with sine, well, the first derivative is cosine. The second derivative is negative sine. The third derivative is negative cosine, and then you'd repeat. The fourth derivative would take us right back to the original sine x. So that's going to help us a lot. So when I look at c, remember, c is literally being used for the coefficients. So just when we come back in a few minutes, so we don't confuse the letter c, we'll make this function d of x. So we don't have c and d mixing together here. So d of x will be cosine. But right now, for function b, the first coefficient would be the original function evaluated at 0 over 0 factorial. Then c sub 1 will be the first derivative evaluated at 0 over 1 factorial. C sub 2, negative, right? I'm sorry, right here, negative sine, so negative sine of 0 over 2 factorial. C sub 3, negative cosine of 0 over 3 factorial. Now I could keep going, but watch what happens here. Sine of 0 is 0. So 0 over anything 0. Cosine of 0 is 1. So I get 1 over 1 factorial. Sine of 0, I know it's negative, but it's still sine of 0. So I get another 0. And now I get cosine of 0, but this time I get negative 1 over 3 factorial. If I just start writing out the terms the way I was up here, look what happens. I get 0 plus 1 over 1 factorial x to the first power, x minus 0, plus 0. Technically here I'd have x squared minus 1 over 3 factorial x cubed. I was using the parentheses here for a moment, but I realized they're not doing anything here. Again, x minus 0 is just x. But here's the point. This continues, but notice what happens. This is 0. This is also 0. If I keep going, my fourth term would be 0. Then I would have plus 1 over 5 factorial x to the fifth. Then my sixth term would be 0. And then my seventh term would be minus 1 over 7 factorial x to the seventh. And this would keep going. Every other term is 0. So in this case, what we should do, and this is what makes this one a little bit trickier than the first problem. The first problem, some people look, and at the end, they just go, oh, well, the derivatives were all 1 over n factorial. So this whole, we kept focusing on this. It just became 1 over n factorial. That was the pattern. That was it. But here, we need to rearrange the sequence, not rearrange, so to speak, but renumber. Instead of n is 0, n is 1, n is 2, n is 3, why keep including these zeros? Let's just get rid of those terms entirely. Remember, technically there was 0, x to the fourth, 0, x to the sixth, but they're all just 0. So let's just rearrange this a little bit. Now we'll let this be 0. Then this will be 1. Then this will be 2. Then this one will be 3. So even though I only went out to here with my derivatives, I noticed the pattern. That's what allowed me to keep expanding these coefficients. And now we could finish this problem. Sine x starting at n equals 0. Well, we are going to get that x term, but let's start out in front. Positive 1, negative 1, positive 1, negative 1. We're alternating signs. I'm going to need a minus 1 to a power, and I need to make sure the first term starts off with a positive, so I could just leave that minus 1 to the n. That covers the positive 1, the negative 1, the positive 1, the negative 1. Some people would argue that sign should be up here. I was just pushing it out in front, but either way, that's going to lead us to the same piece. Now, here's the big thing, everybody. I'm going to get an x to a power, and I'm also getting some factorials in the denominator. But notice two things. First, the exponent on x and the factorial is exactly the same. Not just here, happens here, happens here, happens here. So whatever you work on, whether you're working on the factorial or you're working on the exponent, whatever pattern you find for the general term, you'll get the same thing for the other piece. And now this is where some people, just through a little practice and plugging in, 1 when n is 0, 3 when n is 1, 5 when n is 2, 7 when n is 3, every single time the exponent is twice n plus 1. We're getting 2n plus 1. And then that same thing for the factorial, 2n plus 1 factorial. Maybe that wasn't as obvious, but especially now that we have it written down, you should be able to confirm these will make everything match as you start plugging in. Oops, not to forget my infinity. These will work as you start to plug them in and see that. But big picture, finding the pattern. 1 to 3 to 5 to 7. You keep adding 2, so you need a 2 times n, but then that extra plus 1 to keep everything balanced. If you just had 2n, this would be 0, but it needs to be 1. This would be a 2, but it needs to be a 3. This would be a 4, but needs to be a 5. The plus 1 keeps that balanced. That is the Maclaurin series for sine. And just like you could do, again, I'm not doing this work, I'm just pointing this out. The interval of convergence here would be similar to what we had for e to the x. It would be all real numbers, negative to positive infinity. And you could confirm that with a ratio test. Same way you did up here. The minus 1 absolute value makes it a positive, it's gone. You get an x to the 2n plus 3 over 2n plus 3 factorial divided by this thing. Things cancel. You end up getting an x squared over 2n plus 3, 2n plus 2. But as n goes to infinity, that still goes to 0, so always converges. So I hope you're taking advantage, everybody. That's a perfectly good practice problem for you to work on. If you're still struggling a little bit finding interval of convergence, don't just write that down. Go through, do the test. Again, it took us work to get this power series, but now that you have it, you should be able to run a ratio or root test. Both of these, because they have the factorials, the ratio test would be definitely your better choice. Not a terrible test, and you can get your result. Okay, one last thing before we move into cosine. I want to point out that for a lot of people, you've heard sine, you've heard this before, sine x is an odd function. And for a lot of us, that may go back to pre-calculus, and we think about sine as an odd function. An odd function is one that is symmetric across the origin. That's where we have our symmetry. And there's other pieces. Truly the definition, sine negative x is equal to negative sine x. All that stuff about being an odd function, that is easily proven through a power series. And look at what powers of x are actually left. This is not a coincidence. For those who have taken some pre-calc, you're familiar with those terms, even and odd functions. And initially, those functions were called even and odd because if you only used polynomials, you needed all even exponents to have an even function or all odd exponents to have an odd function. It's not a coincidence that all the exponents are only odd for this odd function. Okay, last thing I just want to point out here, quick little proof. The limit sine x over x as x goes to 0 equals 1. That is a limit. You learn that in Calc 1. And now, we have other ways. If we just plug in, you get 0 over 0, so you could use L'Hopital's rule to confirm that. But in Calc 1, this was where we needed that our units were always radians with trig functions, because this graph, if you're only approaching 0, this piece of the graph right here would basically be identical to the y equals x curve. So as long as you're only in a close proximity of 0, which is exactly what you mean when you take the limit, the sine curve and the y equals x curve are essentially the same, so that they would cancel and you would get 1. An alternative way to do that, to prove that, because that's not really a proof, that's really a demonstration. A way to prove that, use the power series. X minus this x cubed plus this x to the 5th minus this x to the 7th, all divided by x. You would cancel 1x from each term. Here, x cancels entirely, you're left with 1. Here you still have an x squared. Here you still have an x to the 4th, an x to the 6th. As x goes to 0, all those other terms would go to 0, and all that would be left is the 1. So, like I said, I'm kind of trying to point out some other reasons why we care about series, things you can do. And this is really powerful, everybody, for people who go into more upper level mathematics. Sometimes how do you get good results? It's very, I don't want to say too often, but there's a good number of cases using their series representations. The fact that these are nice polynomials, even though they go on forever, that can be a nice way to get results. Okay, so still several things that we want to say, but this is a good place to take a quick break, and we'll come back and do cosine and get some more full problems. Everything we need to, again, a lot of information in this section so far, and we're getting the blueprint for some of the problems, but we still have some more to go, and we'll get that in part 2.